Hello friends, today we will discuss some basics of crystalline solids. These are the outlines of the today's topic. First, states of matter, crystalline solids, types of solids, close packing in solids, space lattice and unit cell, crystal systems, symmetry and its elements, radius ratio and coordination number, defects in crystals. So first of all, let's define matter. So matter is anything which has weight and occupies space. Air around us is matter, we are matter, the whole universe is made up of matter. So in this diagram we have shown three important physical states of matter. First is gaseous, second is liquid, third solids. So from this picture it is very much clear the basic differences between these three states. In gaseous, the particles are far apart. Naturally the force of attraction between the particles will be very less. In liquid, the particles are very close, so they are in a definite volume, force of attraction is more as compared to gaseous state, but they are moving. In solid, the particles are localized, they cannot move, and force of attraction is maximum. So that is why the solids have the definite surfaces. Next, when we cool any gas, there is an increase in force of attraction, and at a particular temperature, when gas acquires surface, it becomes liquid. Then on further cooling a liquid, we can obtain two types of solids. If cooling is very slow, the particles, or you can say the constituents of the substance, get enough time to reorganize, they arrange in a particular pattern, and we get the crystalline solids. But if cooling is very fast, the particles don't get enough time to rearrange themselves, and we get the amorphous solids. So this picture shows the particles are arranged in a particular fashion, and it is a crystalline solid, silica. Next, on the basis of types of bonding between the particles, crystalline solids can be of four types. The first is ionic compounds or ionic solids. So these are solids in which ionic bonds are there between the particles, and particles are ions. Ionic bonds are very strong. So because of this strong force of attraction, ionic solids have very high melting points. Number two, we have the covalent solids. So these are made up of atoms, and atoms are kept together by the covalent bonds. Covalent bonds are very weak as compared to ionic bonds. That is why covalent solids are sometimes soft as compared to ionic solids. They possess low melting points. Next, third type of solids are molecular solids. SiO2, silica, is the example of molecular solids which we have shown earlier. This is the picture of molecular solid which is crystalline again. So these solids are made up of molecules, and there is a very weak force of attraction between molecules. This force of attraction is known as the van der Waals force of attraction. Again, these solids possess lower melting points as compared to even the covalent solids because of very weak force of attraction. Fourth and last types of crystalline solids are metals. So in metals there are positive ions known as the kernels. Around these ions electrons are there, and there is a very strong force of attraction between kernels and electrons, and this force of attraction is known as the metallic bond. Of course, electrons are mobile in metals, that is why metals can conduct current, metals can conduct heat. Next, let us see the close packing of particles in the solids. Here, when I am referring to particles, it means the constituents, and all the solids which we come across are basically made up of three kinds of particles. These are ions, atoms and molecules. Ions, atoms and molecules. So when the particles come together, they try to rearrange within the minimum space. But particles are spherical in nature. Again, some space is left in between. So in all the solids, we found only two types of basic packings. First packing is known as the AB packing. So in the first picture, this is the AB packing, means we have one layer known as the A, then second layer known as the B. The placing of these layers in space is different, and throughout the whole solid this pattern is repeated over and again, means AB, AB, AB. Throughout the whole solid, that only the two layers are repeated, and in between these layers some vacant spaces are left. These spaces are known as the voids or interstitial sites. So this type of packing is also known as the HCP or topaz packing, because topaz is the naturally occurring substance which has AB packing, or we can say which has the HCP packing. So in this type of packing, almost 68% space is covered by the particles and rest is left vacant in the form of voids. The second type of packing is known as ABC. So this is the second picture. What is the meaning of ABC? Means we have three different layers. First layer is A, then B layer, C layer. These layers have different placing in space. The three particles of three layers are not coaxial. They are placed at different places, and again this pattern is repeated throughout the whole crystal. And if we draw lines, we get the pattern known as the CCP, close cubic packing, or it is also known as the FCC, that is face centered close packing. Face centered close packing. Types of unit cells. There are four types of unit cells. First is simple unit cell. This can be drawn like this. In this unit cell, there are 8 points on the 8 corners of the body. Second type of unit cell is body centered unit cell. So in this unit cell, there is one more particle at the central point of the body, and this particle can touch the other 8 particles, and we can draw the picture like this. So this is the body centered unit cell. In third type of unit cell, along with 8 corner particles, there are more 6 particles, one each on one face, and that is why this is known as the face centered unit cell. Every face has one extra particle, and the picture can be drawn like this. This is the top face, right, left, bottom, front and back. Front and back. So this becomes our face centered unit cell. Fourth type of unit cell, which is known as the end centered unit cell, is not so common. It is very rare, and this can be drawn like this. Along with 8 corner particles, we have 2 more particles, and these 2 particles are present on the 2 faces which are at the maximum distance in the structure. Then next we have crystal systems. Now crystals are 3-dimensional bodies. Naturally they have distances along 3 axes, and there are 3 angles. So the 3 distances and 3 angles are known as the crystallographic parameters. Means we decide the shapes or geometries on the basis of these 6 mathematical parameters, 3 distances and 3 angles. If we consider the differences between these 6 mathematical parameters, we come across 7 types of different basic structures present in crystalline solids, and these different basic structures are known as 7 crystal systems or 7 crystal habits. And these we can write. Number first, cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, and last is hexagonal. If we consider the 3 axes and 3 angles, in first type all the 3 axes are equal, all the 3 angles are equal and are of 90 degree. In other structures, we differ between the 3 distances and the 3 angles. The basic differences between these 7 basic crystal systems is of the 3 axes and 3 angles. The symmetry and symmetry elements. First, let us define symmetry. If 2 or more things are completely identical, they are said to be symmetrical, and this phenomenon is known as symmetry. Then we have certain mathematical entities. When we operate these entities on certain substances, they generate symmetry in the substances. For example, we can have a line which is known as the axis of symmetry. If we rotate some substance around this line, two or more similar faces can appear before us, and we say the axis is producing symmetry. For example, let us consider the benzene molecule. If we pass a line through this molecule and we rotate the molecule through 360 angle, 6 times similar face appear before us, and we say this molecule possesses 6-fold symmetry. The other elements of symmetry are point of symmetry. So there are 4 points of symmetry, 4 elements of symmetry. First is point of symmetry, then axis of symmetry, plane of symmetry, and last is rotation axis of symmetry. So let's talk about the plane of symmetry. So let's consider our face. Now if we pass a plane just through the middle of our face, the plane divides our face into 2 identical halves, and we say our face possesses plane of symmetry, because the plane is dividing our face into 2 halves which are completely identical. Similarly, in the diagram we have shown a cube, and if we join diagonally the opposite ends, this plane is dividing the cube into 2 identical halves, and we say the cube possesses plane of symmetry. So it can have many planes of symmetry. We have shown only one plane of symmetry in the cubic structure. Next we have the radius ratio and coordination number. Let's first define what is radius ratio. Now, mostly the crystalline solids, particularly ionic solids, are made up of ions, and ions are of 2 types. First we have the cation, then we have the anion. If we take the ratio of radius ratio, size of cation to size of anion, then we get a number. The number is known as the radius ratio. So size of cation divided by size of anion. So we get a fractional number mostly, and that number is known as the radius ratio. So this number varies between 0.155 to 1, and depending on the value of radius ratio, we can predict 2 things, or from the radius ratio of any crystalline solid, any ionic solid, we can predict its coordination number and its geometry. So let's see what is coordination number. So it is the number of spheres or particles touching a particular particle in any solid. Means how many particles are directly bonded to a particular particle. For example, in case of sodium chloride, if we draw the picture, then we will see that this 6 Cl at ions will touch the 1 sodium cation, and we say the coordination number is 6. Again, in the same structure, if we see carefully, 6 sodium ions touches 1 Cl negative ions, and we repeat that the coordination number is 6 to 6, and if we relate radius ratio to the coordination number, the relation is like this. Let us see the radius ratio, coordination number. If the value lies between 0.1552 to 0.225, the coordination number is 3. If radius ratio value lies between 225 to 0.414, the coordination number is 4. And if the value of radius ratio lies between 0.414 to 0.732, the coordination number is 6. Last, if the radius ratio lies between 0.73 to 1, the coordination number is 8. And coordination number is highly helpful in deciding the geometry of the crystalline solids. Last, let us see the defects in crystalline solids. Now, at NTP we do not have any perfect solid. All solids have certain defects, and it is because of temperature effect on the crystals. But of course, we can have perfect solids or solids without any defect at absolute 0, but practically such a low temperature is not feasible, is not possible. Lastly, any query or any question, please.
You have distinguished between crystalline and amorphous solids on the basis of arrangement of its constraints. Is there any other way also?
Yes,
is there any
very
property which can distinguish between these two?
Interesting question. So we can distinguish between the crystalline and amorphous solids by using so many properties, and melting point is a very important property which we can use to identify whether the solid under consideration is crystalline or amorphous. The crystalline solids have sharp melting points, means they melt at a particular temperature. For example, sodium chloride melts at 825 degrees C. On the other hand, glass, which is an amorphous solid, melts over a range of temperature, so maybe between say 150 to 250 degrees C. So this is the very important property which we can utilize, that is melting point. Yes, please, any other question?
Sir, you have talked about the 6-fold axis of symmetry. Is it possible for the 5-fold axis of symmetry or 4-fold axis of symmetry or 2-fold axis of symmetry? If so, why?
5-fold axis of symmetry are not possible because there are only 2 packings in all the solids, and these 2 packings are HCP and CCP. And if we see the geometry in HCP, there are 6 corners. That is why there is no question of having 5-fold geometry. And in case of FCC or CCP, we have the 4 corners. Of course, there are 8 corners, but one face has 4 corners, and we can generate only 4-fold geometry, not 5-fold geometry. Thank you.